So in this discussion, I'd like to talk about starting with linear systems and sort of where we have an A, a B, and a C matrix. And asking a couple real important questions here as we get into this. One, how far can I actually see? How far can I actually, in terms of the space, access what's going on in terms of the states? That's very much an A and a B question, right? So A matrix being the matrix that it influences all the state variables. B is the matrix that influences the actual inputs coming into the system U sub n. And what I'm also then looking at, in this case, I have some output Y, which is related to C of n and X of n. And the first thing I'm going to care about is, again, how strong can I access things? This often goes by a conversation of what is controllability, but I want to kind of roll through this a little bit. And we're going to do this in the discrete time formulation because it's a little bit easier to see some things that are going to happen out of it. And then the second case I'm going to ask the question is going, all right, well, given that in practice, Y is going to be limiting the amount of which I can see the actual state variables as well, how well can I kind of see what's going on? In other words, if I have to kind of reconstruct the state variables to do some sort of control, what am I going to see here? And so you get a very interesting process that's really kind of neat as you roll it through. The first one starting off with for this case, let's just assume that C sub I is an identity matrix, which means I have a system where I see all the states and they're just straight out of the system. So only thing I really care about is the top equation. Okay, that works out really well. And so then what I begin to build from there is I say, well, let's just see how this evolves in time. And so what would happen if I look at sort of the first sort of M variables, starting off with there's an initial condition that starts off with the initial structure, comes off with the initial input, and then I go all the way down. Well, imagine, just to keep it a little bit simpler, that all my inputs are 1. So it's kind of a generalization of an impulse response. So it shows up only at n equals 1 or n equals 0, and then all the rest of it's just 1s. That's what we're looking at here. And you get an interesting pattern that you certainly see the B show up initially, and then you get all sorts of permutations of the A matrix. Well, that's interesting. Now, if you're in a linear time invariant case, one of the cases that guarantees that is if all of the coefficients A, B, and C for those matrices are not changing with time. Okay, so in their case, I get some very interesting matrices B, A squared B, and so forth as I look down this. And what you know is that once you get the first M sort of construct, right? So we're talking about A being an M by M matrix, that you know that you've at least been able to fully express things, right? This is sort of related to the Cayley-Hamilton theorem that says I can kind of get that for exponentials. I know that's where I'm going with these systems. So as a result, like, yay, okay, I can make sense of this. So these kind of tell me what's in the entire space. And so as a result, I end up being able to create two different interesting matrices. One, controllability matrix, one where it's not linear time invariant. I've got all the matrix forms. It gives me at least a sense over that snapshot in time, and depending on how the variability changes, because a lot of that can get messier. But when it's linear time invariant, it's very straightforward in terms of the matrix. And this matrix is extremely helpful because if that whole matrix is a full rank, right now of M, so then that means that I can reach every one of the state variables. That means I can get access to it. Well, that's cool, because that also means if I can have access to it, if I can reach it, I can control it. And that actually turns out to be something that you can actually build into these systems. So you go, great, that works really, really well. And that's a really important kind of structure for this matrix. And so it gets used all the time, and you'll see this controllability matrix used all the time. You'll also see that if you take that controllability matrix, you related to effectively its eigenvalues, or maybe really effectively sort of that controllability matrix times it transpose, that will give you something that looks much more, that's something now if you look at the eigenvalues of it, tells you the strength of which I can then control along those direct planes or directional axes. That's really very valuable as one digs into this. So then you go, okay, great, so I can actually have an ability to control it, but the problem I will often run into is I have far fewer sensors than I do state variables. Sensors cost money. Sensors cost resources and design. And so you often don't have nearly as many sensors as you do states. And so one of the things you want to figure out is, yes, I only have so many states to work with, but can I actually still be able to see everything? In other words, could I eventually still, given the structure that I have for C and given my A matrix, can I still see everything? Well, again, here we're going to roll down through the first M variables. There's a linear time invariant version of this. And this gives us then something which is what we call an observability matrix. Notice it's kind of a transpose of the controllability matrix. Very, very useful, because then it allows me to then talk about, again, all of these things in sequence, or of course the time varying case that I see below it. And again, if this is full rank, it means that I can fully see everything in the system through the C matrix and the A matrix that I have. So the choice of the way I've built my sensors and the way I'm sensing it allows me to see everything, which is really very valuable, because then it gives me the ability to eventually say I can reconstruct. I can reconstruct what the states are doing, at least sufficiently enough to do a number of different interesting control problems. And so the two aspects turn out to be really important to give us a balance of, what can I see and how can I approach things given very, very, how can I control things given very, very real engineering constraints.